about distribution shift.
Great. Hi, everyone. I'm an assistant professor at Stanford. I did my PhD here at Berkeley, so it's nice to be back. I guess more also as a kind of a means for introduction. I don't consider myself to be at all a theoretician, and in fact, I do a lot of experimental work, including like the experiments that you heard about on the panel, working with robotics. And so here are some videos of some of the robotics work that we've done. Today, I'm not really going to talk about robotics, but a lot of the work that I do in machine learning is like, ultimately, I think will hopefully also help in really core robotics problems as well. So as for some motivation, I think that we've seen some really impressive advances in machine learning and deep learning. And there are arguably super impressive advances as well in image classification, machine translation, things like DALL-E 2 and so forth. But I think that in general, machine learning works well on the training data distribution. And there are a lot of scenarios where the training distribution may not match the distribution of data that the model is seeing at test time. And so what I'd like to talk about today is how we might handle this case where this assumption is broken, and different forms of that sort of distribution shift, when we might be able to handle that distribution shift, when we might not be able to handle it, and some of the assumptions that we might try to incorporate into algorithms when handling distribution shift. So I guess first, let me give a few examples of distribution shift that comes up in kind of the real world. So first, in robotics, we often want to do reinforcement learning from an offline data set. And there's a distribution shift between the policy represented in the data set and the policy that we're optimizing. And it turns out that if you don't account for this distribution shift and try to get a robot to close this drawer here, it ends up doing a behavior that's rather dangerous and is also, of course, doesn't succeed at all at the task. Distribution shift also happens over time. So if you, I guess back in 2009 or so, some folks at Google were trying to predict the incidence of the flu from search queries. And in their paper that was published in Nature, they showed that they were getting a 97 or 0.97 mean correlation with CDC data, which is great. That sounds really exciting. But then a few years later, their model was predicting double the incidence of the flu from search queries because things change over time. And likewise, if you look at the perplexity of a language model over time, the perplexity will increase, especially for things like news articles and even archive papers. So here are a couple examples of distribution shift. To give maybe a couple more examples, those were kind of distribution shifts in reinforcement learning and over time. There's also examples of domain shift or subpopulation shift. So for example, if you want to predict the toxicity of a comment online because maybe you want to make the internet a better place, if you collect a data set for this, you can get around 92% test accuracy. This sounds pretty nice. It sounds like your system is maybe pretty good, maybe good, even good enough to deploy. But then if you look at the accuracy on different subpopulations, then we see that the system actually gets only 69% accuracy on non-toxic comments mentioning the Black demographic. And this is not only problematic from a fairness standpoint, it's also problematic if your subpopulation of users changes over time. And as one more example, in a completely different domain, if you are trying to predict the activities of different molecules, you can get around a 34% average precision on test molecules from training scaffolds. But then if you want to deploy this model to molecules from a new scaffold, your accuracy or your precision drops significantly as well. So I guess hopefully I've maybe convinced you that distribution shift is a problem that comes up in the real world, and it's a problem that we should probably care about in the context of machine learning. If you're interested in these particular kinds of data sets that have domain shift or subpopulation shift and are interested in running experiments on them, I'd encourage you to take a look at the Wilds data set, which has 10 data sets that were informed by domain experts on a wide variety of different applications. Is also put together by Pangwei and Shiori, and if you have any comments or feedback on the data sets, they're really eager for feedback and to try to improve it. Great. So now that we've talked about distribution shift, we need to think about how we might address it. And I don't think that there's necessarily going to be a catch-all solution for all the different kinds of distribution shift. In fact, some kinds of distribution shift are not even going to be possible to be able to handle. And there's also different kinds of distribution shift. So very coarsely, you can categorize distribution shift in terms of covariate shift, which is changes in the P of X, label shift, changes in P of Y, or concept shift. In this talk, I'll focus on covariate shift and label shift. And in particular, I'm going to first try to talk about some approaches that try to address fairly extreme forms of covariate shift. And if we have time in the second part of the talk, I'll talk about some approaches for trying to address label shift and also just get a better understanding of the challenges that arise in label shift. And in the first case, we'll be looking at both supervised learning and reinforcement learning settings. And in the second case, we'll look at long-tailed image classification. Cool. So let's first start with trying to build methods for addressing covariate shift. And before I actually kind of dive into some of the work that we've done here, I'll briefly overview some existing approaches for tackling covariate shift. So there are two high-level classes of approaches that have been fairly successful in practice. The first class of approaches tries to rebalance the data in some way. And so the key idea here is just to upweight or upsample data points that are underrepresented in your training distribution in the hopes that if your distribution shifts, then you'll be more robust to shifts that make those data points more represented. And this includes things like distributionally robust optimization, uniform class resampling, and a variety of other approaches. So this is one class of approaches that basically just tries to reweight the data. One other kind of broad category of approaches tries to learn domain invariant representations. And the key idea here is to learn an underlying representation inside your neural network that is invariant to the domain, such that when you get data from a new domain or data from an underrepresented domain, your model still performs well. And so this includes things like domain adversarial neural networks, invariant risk minimization, and so forth. So these different approaches, they, in general, they've worked fairly well in practice, and they can produce models that are robust to spurious correlations and to domain shift. But they also have some shortcomings. So they may require domain annotations. They may require you to know what domain the data came from. This is practical in some scenarios. It may not be practical in other scenarios, especially if you don't know what spurious attributes arise in your data set. And second, they also don't address more extreme spurious correlations. So what exactly do I mean? Actually, yeah, before I kind of move on, I should also mention that all methods for tackling any sort of distribution shift need to go beyond the standard IID assumptions. Otherwise, we're not going to really get anywhere beyond kind of what empirical risk minimization can do. And so I think that it's important to have this, keep this in mind. And also, I think it means that it's not just the solutions that are unknown, it's also like what sort of assumptions should be introduced into these methods when actually thinking about trying to solve these problems. Okay, so now in this first part of the talk, I want to start with an example of a fairly extreme form of covariate shift. And we're going to start with a really, really simple example where we have this 2D classification problem. And we have two features, feature 1 and feature 2. And our goal is to classify between the positive training examples shown in blue and the negative training examples shown in red. And then there's going to be just covariate shift. And in particular, the gray examples are showing test examples with an unknown label. Now, in this example, we can note that there are a lot of examples that achieve low training accuracy. But they can't all be correct in terms of accurately classifying these test examples. And so we need to think about what feature the model should try to use. And it's worth mentioning that this problem is fundamentally underspecified. The training data doesn't tell us enough about what the correct function is. And it's particularly underspecified because there is distribution shift. If there wasn't any distribution shift, we wouldn't have a problem accurately classifying test examples. Okay, and also feel free to interrupt if you have any questions in the middle of the talk. Cool, yeah.
What do you mean by underspecified here?
Yeah, so what I mean by underspecified is that the training data set doesn't fully specify the correct function. We can't infer the correct function that achieves low test loss just from the training examples.
But you always have that. Just using training samples, you cannot, like even with the IID assumption, even if there is no distribution shift, just using training samples doesn't tell you anything about the test distribution.
Yeah, I think that's a reasonable point. I think that there are certainly scenarios where, like in an IID scenario, where there are multiple solutions. Like you could, like there's a solution that that actually like learns a kind of intuitive solution. There also could be something that just like special cases each of the data points and so forth. So I guess maybe we can think of it under specification in this case as just something where even with like fairly natural forms of regularization, we don't necessarily recover the correct function.
By the way, is it also the case that like in the standard IID assumption, if you had infinite data, then the problem would be solved, right? But in distribution shifts, if you have infinite data,
Yeah.
it's like underspecified. Even if you had infinite data, is that like also?
Yeah, I think that's also a good way to put it. Is yeah, even if you had infinite data, it would still be underspecified. Infinite data from the training distribution. Cool. So given that it's underspecified, I guess, well, first we can think about a few different possible solutions to this. One possible solution is just to try to regularize towards the correct function. If we have some domain knowledge about what feature that we want the model to use, we can regularize towards that solution. A solution like this will require domain knowledge. You need to know something about what the correct function is. And not only does it require domain knowledge, it also requires a way to convert that domain knowledge into a regularizer. And the second point is very easy to do in this 2D example, but maybe much harder to do in higher dimensional examples like an image classification problem. And so this is not a solution that we want to be able to basically develop a solution that doesn't require these two things. Now, an alternative solution would actually be to try to learn multiple functions. So rather than having the machine learning system output just one function, it could actually output multiple functions. And then we would then need some sort of disambiguation procedure to happen at test time with a little bit of added knowledge in order to figure out what the correct function is. And so in particular, one way possibly of doing something like that would be to try to learn a Bayesian posterior over your parameters to try to basically cover the space of possible parameters. But even something like this doesn't really scale well to deep neural networks. For example, one kind of crude way to try to approximate this sort of posterior that works decently in practice is to use ensembles. And even if you apply ensembles to this particular problem, you'll get functions that more or less look the same, that don't actually cover the space of possible solutions. And so in general, vanilla ensembles here are going to show very little disagreement, even on this toy data set. And it could even be much worse in larger scale settings because of simplicity bias or texture bias or something like that. And so what we wanted to do in this work is we wanted to figure out if we could learn multiple functions that do actually better cover the space of solutions. And the way that we're going to do that is we're going to try to learn multiple functions, but add a term that encourages diversity of those functions. And it's challenging to diversify if you only have access to the training data. And so what we're going to do is we're actually going to try to diversify using unlabeled data from the test distribution. And so we're actually going to be operating in the transductive machine learning setting where we have access to unlabeled test data during training. And with that unlabeled test data, we can actually train for the models to make differing predictions on those unlabeled test examples. And so in particular, we're going to train for multiple functions. This could be like an ensemble, completely separate functions. It could also just be a neural network with multiple different heads, which is going to be a little bit cheaper than an ensemble. And we saw that ensembles, like vanilla ensembles, don't work. And so when we train for these multiple functions, we're going to optimize for two different objectives. First, we're going to train for all of the functions to minimize training error. And second, we're going to maximize the disagreement between these different functions on the unlabeled test data. Yeah.
Sorry, just a clarification. So we are thinking about the covariate shift case, right? So if we already have unlabeled data from the
test set, then can't we learn the distribution shift in some sense if we had enough data already?
So if you have unlabeled data from the target distribution, you do have information about what the covariate shift is, but that doesn't necessarily mean that you can get a model that correctly predicts labels, such as in the example that I showed.
Oh, so we are not assuming that the conditional distribution remains the same.
So we are assuming that we have access to the target distribution P of X or P test of X.
Sure.
The one canonical approach to solving this problem would be to use like importance sampling, for example, to basically reweight the data, like I mentioned before. In the case that in this particular example, if you reweight, you just don't have support. You don't have, your training data doesn't have support over your test examples. And so approaches like that won't be able to solve this problem. So we have these two different objectives that we're going to be training our functions on. And in particular, kind of intuitively, you can think of this as training a neural network with multiple heads. We want these heads to be maximally different from each other. And we essentially want to push them apart within the space of near optimal functions on the training, near optimal functions that do well on the source distribution. And the way that we're going to diversify is specifically considering the unlabeled target data and encourage the models to make differing predictions on those unlabeled target data points. Specifically, the way that we implement this diversity term is we minimize the statistical dependence between the predictions from one head and the predictions from another head. And so this will encourage the model to make different predictions on these target examples, because it'll basically just encourage the two heads to be independent from one another. And this sort of loss you can actually compute in closed form for kind of discrete cross-entropy distributions. Yeah.
If you try to maximize disagreement, then the two heads are like necessarily dependent. They're like the first head depends on the second head because they are disagreeing with each other.
So I guess, so one thing that I'll mention is, so you could, if it disagrees on every single data point, then they are going to have a high correlation with each other. And we don't necessarily want them to disagree on every single data point, because our target distribution may still include examples that are from the training, that are in the support of the training distribution. And so we found that a loss function like this works better than something that like just maximizes like L2 or L1 in terms of the predictions, because we don't necessarily want it to be making the opposite prediction on all the data points.
And is that how you also avoid them predicting like opposite labels and canceling the prediction of the ensemble at the end?
Sorry, can you repeat the question?
So in the end, these two heads are used as inside the ensemble of the neural networks, right? And if you had tried to maximize the disagreement, then the ensemble would basically cancel out the two predictions. How do you avoid that?
The ensemble would cancel out.
I don't think she said that they're actually combining the prediction.
Yeah.
Oh, I see.
You haven't explained the ensemble after figuring.
Yeah, sorry, we haven't described the second stage. This is just the first stage. So we're using this to learn multiple functions, and I'll talk about the second stage.
Maybe we can take follow-up questions on this specific one.
Yes.
Cool. So once we optimize these two objectives to learn a set of multiple functions, then we need to actually figure out what function to use. One thing that we could do is just do the typical kind of ensembling thing and average the predictions, but we're not actually going to do that in this case, because if we actually have an underspecified problem, then we don't just want to return a single function. We actually want to figure out which function is the right one. And so that's where the kind of the second stage comes in, where we actually try to pick which function is the correct one. There's a few different ways that you could go about doing this. And we explored 3 of them empirically. The first is just to randomly label some of your test data points and then select the head that's most accurate on those test data points. And I guess I should mention that all of these are going to use some sort of supervision, because as I mentioned before, it's kind of fundamentally underspecified and we need some more information to actually make it appropriately specified. So this is one option, although this isn't going to be that efficient because you may need to sample a fair number of data points. And so something that we could do to actually require fewer data points is actually to query the label for the data point that you disagree on the most, and then use those labels to select the most accurate head. And this should actually seek out the points that are ambiguous and allow you to figure out what the correct function is from that. So this is the second approach. A third approach is if you don't want to require any sort of labels, you could also consider using interpretability methods to just inspect the different functions and try to figure out what those different functions are paying attention to. Interpretability method is kind of an open field, an open problem in and of itself, but we have found in very simple cases, this sort of approach can also work. And this doesn't require any labels on the test data. Okay, so that's the gist of approach. So the first, we learn multiple functions that try to cover the space of solutions. And then second, we then disambiguate and pick one of the functions that we think is actually corresponds to the true function. Any questions? Yeah.
Do you think it is beneficial?
Yeah, so I'm familiar with the model soups work by I think like Luke Schmidt is an author on it. For the problems that we're going to be looking at in our experiments, I don't think that they would work well because we found that on like just even like ensembles will learn very similar functions. I think that you can still see some performance gains, but I think that this approach essentially uses some additional assumptions that allow you to get a kind of a more accurate estimate of the function. Cool. So let's look at actually like what this does in practice. So first we can run this on the really simple 2D example. And in this first case, we just trained a neural network with two different heads and run it on the example shown here. And what we see is that we get one function that pays attention to the first feature and one function that pays attention to the second feature, which is pretty nice to see. We can also give it more than two functions. And so in this case, we just gave it a large number of linear functions, and we see that it covers the space of functions that are consistent with the training data. So those are kind of some visualizations on the 2D example. And then we looked at some experiments on more realistic data sets. So the first experiment that we looked at is we wanted to construct some examples that have this fairly extreme form of underspecification. And so what we did is we took some data sets and constructed them to specifically have a complete correlation or a perfect correlation between a spurious attribute and the kind of core feature that you care about. And we wanted to construct these data sets to essentially be a more challenging version of some of the spurious correlation data sets that are already out there. And then the test data has imperfect correlation or no correlation at all. And so you're going to be seeing a lot more of the kind of other corners that are grayed out that aren't in the training data. And then we're going to measure both average accuracy and worst group accuracy. And what I mean by group is essentially just one of each of these quadrants. So a group corresponds to the kind of a particular setting of the attributes. And then in these experiments, we'll take the div-dis method and we'll just give a neural network with two heads, and we'll give it 16 active queries for disambiguation. Now, in our initial experiments, we'll compare to 3 different methods. We'll just compare to standard ERM, standard neural network training. We'll also compare to 2 upweighting approaches, JGT and group DRO, that upweight examples with the highest error or upweight the group with the highest error. I should note that none of these 3 approaches are designed to handle this very challenging problem setting. In general, there actually, to our knowledge, really aren't methods that are designed to handle this sort of setting. And so these are just going to illustrate how difficult the problem is. And so experimentally, if we compare the performance on 4 of these different complete correlation data sets, we first see that these prior methods struggle as we would expect. So in some cases, they're doing worse than just random guessing because they're binary classification problems. And in contrast, kind of the div-dis approach is able to provide very substantial improvements over these prior methods. On 3 out of the 4 data sets, it gets a more than 25% improvement. And on the 4th data set, it also sees a large, like an 8% improvement in worst group accuracy. Now, these comparisons are not, they don't have the same assumptions as div does. They aren't using the labeled queries. And so we could also consider giving a few labeled examples to these prior methods and see how they do. So in particular, we'll compare to 2 methods that could use these labeled examples. First is just to combine, like do ERM, but on a mix of the training data set and n minority examples from the test data or from the target distribution. And then we'll also compare to an approach that was kind of recently proposed in a paper, which just corresponds to running ERM and then fine tuning the network on n examples from the target distribution, which are balanced by group. And if we look at basically how these 2 methods in div-dis perform as we increase the number of samples, labeled examples that we get from the target distribution, we see that these prior methods require many more examples than div-dis because they aren't explicitly trying to learn the functions that cover the training data a priori. And so div-dis is much more label efficient. And even if you have 128 labeled target examples, it's still outperforming these somewhat naive approaches for using these labeled examples. And this is on the Waterbirds completely correlated setting. Cool. So the first experiment was on completely correlated data. In the second experiment, we're just going to look at some of these previously proposed standard robustness benchmarks for robustness to spurious correlations. And one thing that prior methods have done on these data sets is they often tune hyperparameters using information about the spurious attribute and about the distribution shift. And so in particular, if you take these methods and tune their hyperparameters with respect to the worst group accuracy, which requires group labels, they do a lot better than if you tune them with respect to average accuracy. And in particular, we see that in kind of the first column, the accuracy is a lot higher than in the second column. And so this means that they essentially require access of group labels. They need information about what the spurious attribute is a priori in order to tune the hyperparameters. And this isn't something that we want because these methods, or in many cases, we may not know what the spurious attribute is at the beginning. And we instead want to be able to build models that are robust without that information. In contrast, we find that div-dis actually doesn't need access to group labels, so it performs well even if you tune with respect to average accuracy. And to kind of dive a little bit deeper into this, if we look at the performance for different values of the hyperparameters after tuning on the source distribution, the target distribution, sorry, if you look at the performance in terms of the source distribution accuracy, the target distribution accuracy, and the worst case target distribution accuracy for different values of the hyperparameters, we see that it's very, kind of the trend is very consistent across these different distributions. And this means that if you essentially, because these look very similar, this means that if you tune for one distribution, you'll also perform well on the other distribution. Cool. So essentially, it's yeah, less sensitive. Yeah, go ahead.
Do you have a sense of which is it the majority class or is it the minority class on which the existing methods fail or like don't do?
Yeah, in general, it's typically the minority class. And so worst group accuracy is going to measure whatever group it's doing the worst at, but in practice, we see that it's usually the minority class. Cool. And then the last experiment we looked at was domain shift problems. So we took one of the WILDS data sets, and this is this chameleon data set where you're trying to predict if the cells are tumorous or not. The label distribution, the training data is from in-distribution hospitals, and then you hope to generalize to new hospitals, which is a pretty natural use case because you don't want to necessarily have to train a model for every single hospital. There isn't complete correlation in the setting, again, like the second experiment. And in this case, we're compared to different domain adaptation methods that have been kind of proposed for this particular problem setting that use unlabeled data from the out-of-distribution hospitals. And we also see that div-dis is able to perform well on this kind of domain shift setting. So it doesn't only work on subpopulation shift settings, it also works well for domain shift settings. and compares favorably to these prior methods. Cool. So I guess the summary of this approach is instead of trying to learn one function where we try to learn kind of multiple different hypotheses underlying the training data. And we do that by trying to minimize training loss, but also trying to kind of train for functions that make differing predictions on the test data. This allows us to handle underspecification in the data and allows us to perform well, even if our training data set is completely correlated, and also in scenarios where we don't have group information available. Yeah.
For the beta experiments, like the mean shift or cases where it's not perfect correlation, like how many heads do you typically find that you need to use?
Yeah, so actually basically in all of these experiments, we're just using 2 heads. And so we, at least in these examples, we found that 2 heads works well. In scenarios where you have more than one spurious attribute or more than one source of variation, I would expect that more heads would be helpful because you may need to learn functions that pay attention to each of those spurious attributes. At least in these data sets that we looked at, we haven't seen that to be the case, although you can certainly imagine data sets that are like that. And that's one of the things that we're looking into is like, can we handle those cases where we have lots of spurious attributes? And potentially even like here we are learning a discrete set of functions. You could also consider learning a continuous set of functions as well. And that's another thing that we're thinking about right now as well.
And related, would you expect there to be like a combinatorial exclusion of necessary heads if you have more attributes, or is it you would expect each head to pick up just like one attribute as opposed to a combination?
Yeah, it's a good question. So I guess I don't think we have a good understanding for why this is the case, but we do observe that it seems to generally learn to use one feature rather than using a combination of features, at least in terms of the first few heads that it uses. And so in that case, if you want the model to pay attention to one feature rather than a combination of features, then I think you would probably only need linear number of heads in the number of features, or in the number of spurious features. Although if you have a case where ultimately it needs to use a combination of features, then you would probably need a combinatorial number of heads in the number of spurious features. I do think that fortunately, a lot of data sets aren't going to have a large number of spurious features in practice. And so that would mean that you ultimately don't need that many. Also, if you have a way to learn a continuous set of functions rather than a discrete set of functions, that would also make this more practical. Although as you have more and more functions, the disambiguate phase will get more expensive. You may need more labels to disambiguate and figure out what the correct function is. Yeah.
If you wanted to extend this to multi-label classification, how do you think you'll be able to enforce disagreement between your competing hypotheses?
Yeah, that's a great question. So far we've primarily looked at binary classification problems. And if you have multiple different labels, then there's multiple different ways that you can make diverse predictions. I guess, one naive thing that you could do is just train a different function for each label. And that's maybe somewhat dissatisfying, although it's not completely unreasonable, I think, to do something like that. And then I guess we haven't really explored it empirically, so I don't have a good sense for if it would work out of the box or not. Yeah.
Could you go into your table and experiment?
Yeah. This one? Or yeah.
What is regular plot?
Yeah, that's a great question. So we found that it's sometimes helpful to add a regularization term. And in particular, what we did is we just regularized the marginal label distribution of each of the heads to be the same as the empirical P of Y. And so in particular, if you one instability that can happen is it can just decide to, like, for one head, just label everything that's unlabeled as like 1 and the other head labels everything as 0. And that's an effective way to diversify on the unlabeled examples. But that differs from the kind of the label distribution that you see in The training data, you don't see such, like, not everything is labeled as 0 in the training data. And you would also expect on the test data that not everything would be labeled as 0. And so we added a light regularization term to encourage the predictions to follow the label distribution of the training data set. If you have any knowledge about the target label distribution, then you could also incorporate that knowledge. We found it wasn't super sensitive to this regularizer. And so if you set it to be different label distributions, as long as it wasn't like all zeros or all ones, it seemed to work well. We also see that even without the regularizer, it also performs pretty well. Yeah.
I was wondering if like 0% might be a reasonable thing for first group baseline rather than 50%.
So yeah, it's not like, I would not be surprised if some of these baselines were getting 0% on worst group accuracy, and indeed we see ERM is getting 7% on Waterbirds. Yeah. And that just means that it's paying attention. In this case, the Waterbirds data set, you're trying to predict the foreground bird, and the spurious attribute is the background. It's relying on the background in the worst group.
Yeah.
If it's just predicting on the background, then it will get 0%. So it's not, yeah, I definitely am not surprised that that it can be close to 0% in some of these cases. I guess I'm not sure. Does that answer your question?
Yeah, that's
Okay, one other thing that maybe I'll mention here is that the one thing that I like about this method is that in our toy example, even if you add other dimensions to the data set, it's only going to diversify in the parts where you have unlabeled test data. And so this means that you won't require, as you increase the dimensionality of your data, you're not going to require more and more heads. You're only going to require more heads insofar as your training data distribution differs from your test distribution. And I think this property is really important because we often do have high dimensional data. And I think this is one of the reasons why a method like this works well. And methods that try to learn like Bayesian posteriors, for example, don't work well because they're trying to learn things that are diverse along all possible dimensions of the data. Yeah.
Quick question about this experiment. So to make sure I understand this, do you also have access to these test points that are not like in this part of the space that you talked about?
Yeah, exactly. So yeah, the test data points aren't visualized here, but we do have access to them. And we only have access to the unlabeled. Yeah.
Could you use this method to like detect distribution shifts that are meaningfully similar?
Yeah, absolutely. So we haven't run experiments on this, so it's like anything I say here will be speculative, but I think that I certainly could see a method like this being used to detect distribution shifts, being able to detect spurious correlations. Because if it's able to diversify, then that means that there is a distribution shift. Versus if it struggles to diversify, then that would suggest that there isn't a distribution shift because it's a lot harder to diversify on these examples when you also have to minimize training error than it is to diversify on these examples. That's it. We haven't ran experiments specifically on that, so we'll see what happens. Yeah.
So I'd like to, about your comment about like the diversification of Bayesian posterior, could it be the property of the linear classifier? So the linear classifier has a mean seeking property, right? So as you go away from the mean, the classifier is more uncertain. So if you can actually quantify the epistemic uncertainty of the classifier, maybe you could obtain something like this from a Bayesian posterior as well.
Well, possibly, I could certainly see something like that helping. But I still think that by considering by using the unlabeled test data, you don't have to diversify nearly as much. You only have to diversify along the axes that the test data differs. And so if you had you basically just have a much narrower thing a narrower space of functions that you're trying to represent compared to a Bayesian setting, a Bayesian posterior when you have high dimensional data. And so I think that in and of itself will make this a lot easier than when you don't have unlabeled test data.
I noticed as well in this figure, I'm not sure if it's just in this figure or your other experiments as well, but it sort of seems like it converges to the max margin classifier with respect to the training distribution, and then it performs diversity. So I was wondering, firstly, if you think that seems to happen in general, and second, then what do you think would happen if you started with a max margin classifier? Say you trained the ERM, and then how would you take that ERM, how would you diversify that ERM now? Because it seems like it's kind of what's happening here.
Yeah. So we also noticed this. So that was the case of linear functions. We also noticed this in the case of neural networks as well. We see that it kind of converges there and then diversifies. We haven't specifically analyzed if it does that in the higher dimensional settings, but we have actually ran experiments like the ones that you mentioned. They're not in the paper, but we ran experiments where we first just trained the network on the training distribution, and then we've just fine-tuned for like a pretty short time period with the div-dis loss. And we actually found that that actually works quite well. And you can even just like fine-tune the heads on top. You don't even need to necessarily fine-tune the whole backbone, the features as well. And that's something that I think is actually quite a nice property, because it means that we don't necessarily need access to the unlabeled test data right at the beginning of training. We might just be able to first train our big network or whatever, and then do this little step to diversify once we get that unlabeled test data.
I was also wondering how you think that procedure compares to also the paper you mentioned of the retraining the last layer is sufficient. Like, how would doing that sort of compare to what they're doing in that paper?
Yeah, so the reason why we actually ran that experiment is we saw that paper and we're like, oh, maybe we can do something similar with this sort of loss. And so yeah, that was I think that it in some ways, I mean those experiments are still somewhat informal. We haven't put them in the paper and they've been fairly recent, but in some ways I think they do kind of confirm some of the findings from that last layer retraining paper. And and I guess this is the paper that we're talking about. And I do also think that there's still some benefits of the div-dis method over this other paper, because well, first it's more label efficient, at least on this data set, and it may also be used for like detecting distributions if possible.
And I'm sorry for having so many questions. If someone else has a question, they can go. But I kind of a little bit more of a philosophical question. Like, do you think that in non-IAD settings, it is sort of like reasonable in general to expect that building on ERM is going to give us something good, or do you think that in general for non-IAD settings, they require?
Yeah. I guess I do feel like so I think that like I like the idea of learning multiple functions. Like it seems like under specification may come up a lot in realistic settings. Even if you can also have under specification just because you don't have infinite data as well. And so that's something that I think is completely different from ERM. Like a lot of machine learning just has this assumption that we're just going to learn one function and ship it basically. So there's that. I'm not sure if I have any like insightful thoughts beyond that though.
Thanks.
Yeah. Cool. So that's a summary of div-dis. Now, as a bit of an aside, there's also a question of whether we could try to do this for reinforcement learning. And the project that I'll talk about, actually, this is an older project. It actually came before div-dis and was in some ways actually some of the inspiration for div-dis, but yeah, I'll kind of talk about it now. So in this reinforcement learning setting, we're going to be looking at a setting where we have one training environment, and our goal is to be able to generalize to new test environments, such as we want this walker to run forward in the simulation, and we want to be able to handle cases where it encounters an obstacle, or there's a force that is kind of applied to the agent, or the joints are disabled. And kind of some of the intuition here is that if we learn multiple solutions to the training data set, then some of those solutions might work well out of distribution. So if, for example, our goal is to get from the green triangle to the the green triangle to the red circle, then if we, for example, encounter an obstacle at test time, then one of those solutions still works in each of the two cases. This is still, like in DivDis, is going to require us to adapt our solution set at test time. But it gives us some kind of recourse. It gives us kind of a contingency plan when we encounter these out of distribution scenarios at test time. Now, this is making a couple assumptions. First is making an assumption that we can adapt with some data in the target environment. And second, it's assuming that the changes between the training environment and the test environment are somewhat localized. And kind of more formally, what this means is that the optimal policy in the test environment needs to also do well in the training environment. And if this property holds, then that means that if you learn multiple kind of near optimal solutions in the training data set, then it should actually, one of those solutions should do well in the test environment. Cool. So then there's this question of how to learn multiple different solutions. We're going to do something very similar to DivDis, where we're going to train a set of policies that all do well on the training environment, and we're going to encourage those policies to be diverse. It's important that we can actually control which policy that we use. And so in this case, instead of learning a discrete set of functions, we're going to use a latent variable to basically index into the policy rather than just learning separate heads. In this case, the latent variable will actually still be a discrete latent variable, but in principle, the same formalism could apply to continuous latent variables. And then in terms of actually getting these policies to be good, we can formulate a constrained optimization. And so specifically, we can formulate an optimization problem that looks like this, where we are going to encourage the policy to be near optimal. And we're going to try to maximize the mutual information between the states visited by the policy and our latent variable. And this is going to encourage the policies to be diverse in a controllable way, because essentially you can, well, there's a few different ways to look at this, but if you have high mutual information, that means that Z is basically predictive of the states that are visited. And also that the states have high entropy. Cool, and then in practice, there's ways to kind of actually kind of massage this objective into something that you can actually optimize with a reinforcement learning algorithm. And then at test time, once we have this kind of set of diverse policies that are indexed by Z, we can then just roll out different policies with different Z's in our test environment, and then return the policy that performs the best in our test environment. Cool. So we refer to this as structured maximum RL, in the sense that we're doing maximum entropy, but specifically in a way that is controlled by the second variable. In our experiments, we tested whether this method of learning diverse policies can allow us to be robust to different kinds of obstacles, perturbations, and motor failures. And we compared to just standard reinforcement learning with software critic, a method that only optimizes for diversity and doesn't optimize for the task loss, and also a method that is designed for robustness, which is called robust adversarial reinforcement learning, that basically injects adversarial perturbations into the agent during training. In each case, we're going to be measuring 5-shot generalization, and we're going to look at basically what 5-shot performance looks like as we increase the distribution, as we increase the difference between the trained environment and the test environment. And so for all the methods, we'll expect performance to go down as we increase the distribution shift. And so we do see that trend. I guess in the case of motor failure, we actually don't see a trend like that, but in the case of the obstacle and the force perturbation, we do see trends that look like that. And overall, the approach that I talked about before is able to do better than this prior robustness approach shown in green. And it also does better than only optimizing for the task objective or only optimizing for diversity. Yeah.
5 is the number of test rollouts here. 5-shot.
Yeah, 5 is the number of rollouts that we get in the test environment.
Okay, and why do you think you don't see this in motor failure?
I think that, well, there's it could be an artifact of the simulation. It could be that we're not. I guess. Well, so I guess with the motor failure, I was gonna say that maybe we're not. Like maybe we didn't pick a motor that's like really essential to these particular policies, or maybe we didn't have the motor fail for a large enough period of time. It's possible also that the simulation, we're using the Majoko physics engine here, and it's possible that it just didn't have too much of an effect on the policy. Yeah.
So the Z here is, if I understand correctly, not T dependent, right? It's a fixed.
Yeah.
And so you're looking at the mutual information not between the entire trajectory and Z, but rather between each state.
The state.
Yeah, you're right. So it's kind of like is it correct to think of it as partitioning, trying to partition the state, so that depending on Z, you use a completely different set of states for every.
Yeah, so it'll encourage it to visit different states depending on Z. It's possible that to solve the task, you have to pass through some certain states, and so it may not be able to optimize that fully. If it may not be able to fully have them be completely disjoint sets of states. You can also replace that with trajectory as well instead of states. Although in those cases, it's.
Would that be good? I mean, it doesn't say if that's like just condition optimized, or if that actually would be like bad for this.
It doesn't work. So
I wanted to actually.
We want to be based on states. Yeah. So kind of the intuition there is sort of objective. There's a few different ways that you can decompose this. The other way is to do h of z minus h of z given s. And you can think of it as basically trying to be able to predict z from the state or predict z from the trajectory. And it's actually, if you give it the full trajectory, it's going to be very easy to predict z, even with a very small difference. And so it's using the states here. It's actually a lot easier to optimize the trajectory version of this than it is for the states, and the states works a lot better.
Thanks.
Cool. We can also see some videos. This is one of the cool things about RL. So here's the goal is to reach the goal position in the green dot. If you just train 5 different policies with soft microcritic, you get some policies that look like this. They aren't very diverse. And then if you give it, if you put a wall in the way, it understandably struggles to get over the wall. In contrast, if you train with this objective that tries to encourage the policies to be diverse, you get some diversity. There's only so many ways that Cheetah can go from A to B, but in some cases you see it kind of goes more on its back leg. In some cases it's more flat, and in some cases it also flips over. And in this latter case, we see that the flipping over strategy is actually pretty effective when there's an obstacle. Cool. So yeah, the takeaway here is that instead of just trying to use machine learning to return one function, we can use it to learn diverse classifiers and diverse policies that allows us to very quickly adapt to certain OOD situations. Yeah.
So the examples we have here, like the latent space is relatively low dimensional, like the state space is relatively low dimensional. Were you able to get this to work as well for like sort of pixel valued observations, or is that like there's just so many of them that it's hard to define a good notion of mutual information?
Yeah, it's a good question. So this work is from 2020, it's from 2020, so 2 years ago, and we were building upon the diversity is all you need, the Diane method. And I guess we personally didn't try anything with image observations. I don't know of methods for learning diverse skills that work well with image observations. I haven't fully kept up to date on the literature there, but from what I've seen, I don't think I've seen anything that works well with images. Maybe proto-RL, maybe. I can't remember if they had image experiments. In principle, none of the ideas are specific to low-dimensional states, but yeah, I don't have a good sense. I think it's probably a lot harder with image observations if you haven't tried it.
Why does the Diane line always do
that?
Or not always, but like in a lot of the environments, it seems to do better the further you cut from the training environments.
I guess I mean, it seems like it's flat in a lot of cases, except for the top right case.
Yeah, the top right and the bottom left. I was just
And the
curious if
bottom
you like
left,
knew what was
yeah.
going on in those environments.
Yeah, I don't have a good sense for why that might be the case. In the motor failure case, I actually hadn't noticed that before. I think that it's optimized for it's not really optimized for the task at hand, and so we wouldn't really expect it to be solving the task necessarily. And so I suspect that there are there are some environments where it happens to learn a skill that's good for that perturbation, and there's some environments where it doesn't. So I don't think that there's any particular specific trend here. Yeah. Cool. Okay, so we talked a little bit about covariate shift and also distribution shift, local distribution shift in reinforcement learning. Now we have a bit of time, so I'll talk a little bit also about label shift. So one thing that comes up a lot in supervised learning settings is long-tail distributions, where it looks like all yellow off the curve. On my screen, it's green on the big data and yellow on the small data. But we kind of observe in practice that on the long tail, deep neural networks and machine learning systems in general often perform very poorly on the tail of the distribution. And one hypothesis that we had for this, for why this might be the case, is that, I mean, first in general, the tail has less data. But in principle, it should be able to use the data that it has from the head of the distribution in order to learn better for the tail. And so our hypothesis is that there are certain class agnostic invariances that your model should contain. So for example, it should be invariant to lighting. And our hypothesis is that it probably learns these invariances well on the head of the distribution, but it doesn't automatically transfer those invariances to the tail of the distribution. And we suspect that maybe if it did successfully transfer these invariances from the head of the distribution to the tail, then maybe it would actually be more successful on the tail of the distribution. Now, one thing that's kind of cool about this hypothesis is that we can actually run experiments, or maybe what Nadia would call simulations, to test this hypothesis. And in particular, what we'll do is we'll create a synthetic data set that has these certain transformations in the data set. And we'll train models and then evaluate their invariance to this transformation. And in particular, if we construct this transformation ourselves and have access to this transformation, then we should be able to test invariance to that transformation. And so in particular, we'll look at a few different transformations, background shading, dilation and erosion of these images, as well as rotation. And I guess in this case, we're actually, the long tail data set itself, the original long tail data set is from this KMNIST data set, which is actually naturally long tailed, although it's going to be synthetic in that we're actually adding these transformations to the data set so that we can specifically test whether or not the invariance is transferred. And so what we're going to do is we're going to measure invariance with respect to class size. And so to measure invariance, we're going to be looking at the expected tail divergence between the distribution before and after the transformation. And we'll be measuring this as we increase the number of examples. And if it was transferring invariances successfully, then we would expect that the invariance would be, or that the value would be low for all classes, even if classes that have a small number of examples. Whereas if it's not transferring invariance as well, then we would expect to see kind of a downward trend where we have worse invariance for smaller classes and better invariance for larger classes. And what we see is both for kind of empirical representation and also for an approach that kind of resamples the data. We see in both of these cases, we see this downward trend where for the larger classes, it learns the invariance as well. And for the smaller classes, it doesn't learn the invariances. And this could explain, this could provide one explanation for why it may not, for why these models may not generalize well on the tail of the distribution. So yeah, in general, the evidence here suggests that invariances aren't transferred across different classes in deep neural networks. We also explored one way to try to encourage the model to transfer invariances. There are probably lots of different ways to do this. Yeah, so actually, maybe we'll just skip this part. There's lots of different ways to do it. We use a generative model to do it, but there are other ways to do it as well. And we find that it kind of improves invariance overall and improves performance. Cool. So to summarize, I talked about learning diverse functions. I also talked about kind of label shift and invariances. If you're interested in this distribution shift, I'd encourage you to check out the WILDS data set. I think we should go into the break, but I'm happy to chat offline afterwards. Thanks.
So I think we come back at 4. We have a 10-minute break or so now. That's how you can come ask questions.